Then, as it is mentioned in the title, I will discuss the dynamics of non-spherical particles in random or turbulent flows. And those particles, when they are immersed in a fluid, they rotate and they orient themselves according to the velocity gradient. And the properties that one would like to investigate is the main properties is the PDF of orientations and how this PDF depends on the properties of the flow. Of course, there are many instances in nature where this kind of problem is important. Here there are just a few examples. In the biological sciences, there are certain bacteria which can be modeled as elongated particles. In the atmospherical sciences, ice particles play an important role in certain processes like rain formation and radiative transfer in clouds. And another application is turbulent drag reduction. Indeed, it is well known that elasticity is not necessary to get turbulent drag reduction. The orientability of rod-like polymers is sufficient to obtain a considerable reduction of the turbulent drag. Now, of course, these are very nice and important applications, but they are also very difficult. So the first step to investigate the properties of a suspension is to describe what one isolated particle does in a given flow field. And this has been done for laminar flows in a very extensive way. There is a huge literature. The equations of motion for the spheroids were obtained by Jeffrey already in 1922. Then it was generalized by Greve for particles of a more general shape. Then Hinch and Liel studied the influence of Brownian motion. Zeri studied the laminar unsteady flows. These are only just standard references. There is a really big literature on this problem. On the contrary, for turbulent or chaotic flows, there are some papers, but not so many on this subject. There are some experimental papers, but in experiments, they have to consider particles whose size is in the inertial range, I believe for practical reasons. So the problem of modeling their motion is a little bit more complicated because the velocity gradient fluctuates over the size of a particle. Small particles which are below the Kolmogorov scale can be studied in numerical simulations, and this has been done in channel flows, in some chaotic flows, and there is a recent paper by Alain in isotropic turbulence. And as far as the theory is concerned, I was surprised to learn that there are very few papers, very few results on this problem. There is mainly a work by Kostya-Turitsyn, where he considers mean shear plus isotropic fluctuations. And again, a recent paper by Alain and Michael Wilkinson, where the vorticity is modeled by means of the Langevin equation. So what I'm going to present is a very simple example where the PDF of orientations can be calculated exactly. As you will see, there isn't any amazing new physics emerging from this study, but I still believe it may be interesting because of what I mentioned, because there are very few examples, very few analytical results on this problem. So the starting point is Jeffrey's equation for the dynamics of a non-spherical particle. I will consider particles which are bodies of revolution. The density of the particle is the same as the density of the flow. And the velocity field is incompressible. And the velocity gradient doesn't vary much over the size of the particle. Then there are a couple of other assumptions behind this equation. Inertial effects are neglected, and also hydrodynamical interactions between different particles. So this is an assumption which makes sense when the solution is dilute enough. And also there aren't any other external forces like an electromagnetic field influencing the dynamics of the particle. So under these assumptions, the motion of the particle is completely described by the position of the center of mass, but in this case it will just follow a fluid trajectory. and the orientation vector, which solves this equation. There are two parts. The first two terms on the right-hand side give the rotation due to the velocity gradient. The last term is just Brownian fluctuations due to the collisions with the molecules of the fluid. And you may want to remember for the remainder that d here gives the intensity of these Brownian fluctuations. Here, kappa is a kind of effective velocity gradient. As you can see here, the asymmetric part and the symmetric part of the velocity gradient are combined with a given weight, gamma. When gamma is an absolute value which is smaller than 1, the dynamics of any body of revolution with this property can be mapped, is equivalent to that of a spheroid with a given aspect ratio. And for a positive gamma, one gets prolate spheroids. For a negative gamma, we obtain oblate spheroids. And the special cases are spheres down equal to 0, and two limiting cases are rods and disks. Now, I'm going to start with this problem, this equation, for a given random velocity gradient. And I will consider an axisymmetric random flow. Why? Because the simplest random flow we could imagine is an isotropic random flow. But for this problem, the solution would be completely trivial because there is no preferential orientation in an isotropic. Yes.
What does the column in the first equation mean?
Yes, and maybe it's not a good notation. It's just this one.
Yeah.
It's just a K, I, J, N, A, I, N, J. It's a double saturation of the matrix with the vectors. And so then the next step after an isotropic flow, the simplest anisotropic flow, is an axisymmetric flow.
How gamma converges in unity? It's intuitively. Could you explain?
Intuitively, no. Brandon has shown some examples of very long particles.
But it's rod. Very long is rod.
He shows there's a combination of spheroids linked by some rigid constraint. He also says that maybe they will not be finding each other. The particles are satisfying this problem. But he showed that in principle it can exist. More precisely, I will consider a Gaussian flow with a zero mean. This can always be achieved by considering the reference frame moving with the mean flow. So the complete statistics, the entire statistics is defined in terms of the second order correlation of the flow. And I will consider the case where the correlation time is small. This is a good approximation when the correlation time of the flow is small as compared to the stretching time of the flow. And as for the spatial dependence, I will consider a flow which is statistically invariant under the following transformations. So there is a given direction lambda, which we may interpret as a mean flow, as the mean flow direction. And the flow is invariant under rotations around this direction and under reflections with respect to planes perpendicular to the direction lambda and containing the direction lambda. So on these assumptions, the form of the correlation is this one, where there are four independent parameters, A, B, C, and D. Let me stress the fact that when B, C, and D are equal to 0, we recover an isotropic flow. So A here will give the intensity of the isotropic part of the velocity gradient. B, C, and D gives us the anisotropic component of this flow. If we choose for, let me say, unfortunately it seems there isn't a simple way to combine all these parameters in a way as to give a single anisotropy parameter. But still, the four coefficients are related in a simple way to the components, to the variances of the components of the velocity gradient. And since these variances must be positive, the four coefficients must satisfy some inequalities. Now, if we assume this kind of statistics, the evolution of the orientation vector will be a stochastic differential equation where there are two sources of noise, Brownian motion and the velocity field. And so it makes sense to define a probability density function of the orientation vector, both with respect to noise and with respect to the velocity field. Now, if we use the assumption of a short correlation in time, it is possible to derive a Fokker-Planck equation for this probability density function. I didn't write here, and where the coefficients alpha j and beta j depends on gamma, the parameter related to the geometry of the particle, and of course on the anisotropy of the random group. If I didn't write here the two coefficients, because actually it makes much more sense to move to spherical coordinates given the symmetry of the flow of the problem. If we take the third axis in the same direction as lambda, as the mean flow, theta will give the orientation of the particle with respect to the mean flow. So if we move to spherical coordinates, the Fokker-Planck equation for the probability of orientation takes this form. A couple of comments on this slide. This equation must be solved with periodic boundary conditions. In this particular case, these conditions imply that the probability current is zero, so the problem is easier to solve. Then it's interesting to note, but it's not unexpected, that the coefficient in front of the second derivative of the probability with respect to phi does not depend on phi, so it is possible to write an equation for the marginal probability of the angle theta only, and so at long time the probability depends only on the angle theta and not on the angle phi, which is expected due to the symmetry of the profile. And also from this equation it is possible to derive a simple equation describing the evolution of the angle theta. This equation still remains not very easy to be solved because the coefficients are an algebraic combination of trigonometric functions, but still can be useful for some asymptotic predictions or just to simulate the problem. It becomes a one-dimensional differential equation. Now let me come back to the Fokker-Planck equation for the PDF. It can be solved for the stationary solution, of course, and I'm writing here the form for rods, and then I will comment also on the more general particles. This is the form of the probability of the angle theta. One first comment is that the intensity of Brownian motion appears always, gives the same contribution as the isotropic part of the flow. So in general, this contribution will be negligible as compared to the turbulent flow, and in any way, contrary to what happens in laminar flows, there isn't any gain in considering the Brownian motion in this problem. The second point is that the isotropic contribution should be comparable or smaller than the anisotropic one to see some dependence on the angle theta. Otherwise, the dependence is very weak and the PDF becomes flat. So the coefficient A giving the isotropic part shouldn't be too big if we want to see something interesting. A third remark is that if we were to consider particles of a general shape, the functional form of the PDF will remain exactly the same, only the coefficients will change.
There is no way to make 4a plus d capital minus b plus d close to 0. I mean, the sum of the first focus. No way there is some inequality.
Yes.
Okay,
sorry, it was here. It's here. It's not really here, but it's related.
So no singularity.
No. And
no, that would be singularity at theta 0. That would be just dropping in the
maybe in a limiting case, but and the final comment on this slide is that it looks like in bold, the form of this function, but actually a lot can be understood already from the denominator. The numerator here doesn't really change much the functional shape of the PDF. And as I'm going to show, a lot can be already understood from some simple cases. For example, if we take d equal to 0, we are going to see that the solution is very easy to deal with, and we can understand basically the entire dynamics. So the first example is rods, and I make this assumption. So the PDF has this very simple form, the horrible numerator disappears. And if we have the first kind of dynamics is given when b over c is positive. In this case, the PDF has two peaks at the 0 and phi, so the particle spends most of the time aligned with the mean flow. Of course, the strength, the intensity of the alignment depends on the anisotropy of the flow, and when the fluctuations in the direction of the mean flow are very strong, there can be a considerable alignment. Given that this is the stationary PDF and it does not depend on the initial condition, both the alignment and counter-alignment are equally probable. So the motion is a tumbling motion between the two configurations. But I would like to mention that this tumbling motion is very different from the one observed for shear flows. Because in a shear flow, if you put, for example, a rod in a shear flow, it will immediately align with the mean flow, and then due to some Brownian fluctuations, it will fluctuate around this direction. But if a fluctuation is strong enough to make the angle theta become negative, then the rod will immediately flip and invert the direction. So in a shear flow, it's basically the dynamics is the transition from two unstable configurations. And so if we were to plot the angle theta as a function of time, it will be something like this, then a sudden transition, etc. And so in such a situation, it is clear how to define a tumbling motion and the probability distribution of this time intervals. In this case, due to the random nature of the flow, the dynamics is not as clear as here. For example, this is just a numerical simulation corresponding to this PDF, where the peaks are already narrow enough, considerably narrow. And as you can see, there are instances where the particle is mainly aligned with the mean flow, it goes closer to the perpendicular direction, then it comes back. It's a situation that cannot be seen in the shear flow. And also here it is less straightforward to define a tumbling time and the probability of a tumbling time. Perhaps, and this was suggested to me by Prasad, it's a situation where one could define a probability of persistence in this case. Even one take a threshold at phi half and then can define the probability of being on one side of the other. Now, still remaining in the case d equal to 0, if now we choose a different set of a different range of parameters, we can observe a different dynamics. Here, the particle mainly rotates in a plane which is perpendicular to the mean flow. And once more, of course, the strength of this kind of alignment depends on the anisotropy of the flow. There is a third and last regime which can be observed for this in this range of parameters. And here there is a preferential alignment of the particle, but with a direction which is intermediate between the mean flow and the perpendicular one. And again, the angle depends. The angle depends on the parameters on the characteristics of the flow. Now, as I mentioned, this kind of of dynamics, these three regimes, can be shown, proved easily for this particular condition. But for the general case, for the general axisymmetric flow, it can be easily shown that there are at least 3 minima and at most 5 minima. So the dynamics will be exactly from a qualitative point of view, it will be exactly the same also for a completely general axisymmetric flow, not only for the case equal to 0. The tumbling motion and the rotation in the perpendicular plane will always be possible. If the parameters make this argument positive, we can also have a preferential alignment in a direction which is intermediate between the mean flow and the perpendicular plane. Now, just to conclude, I would like to mention that this dynamic that I described was for rods only, but it can be easily generalized to any kind of particles. I don't plot the details here, but as you can see, the functional shape remains the same for other particles. It's simply the intensity of the alignment becomes weaker when we move, for example, towards a spherical particles. Here is, for example, a case where a rod rotates in a plane perpendicular to the mean flow. As you can see, if I change the geometrical shape of the particle, as long as gamma remains positive, there is again preferentially a rotation in the plane perpendicular to the mean flow, but this kind of alignment becomes weaker and weaker as we move from rods to prolate spheroids and down closer to a sphere. Of course, when gamma becomes negative, and for the same parameters, we obtain a complementary dynamics where the particle is aligned with the mean flow, and again we observe that the disk led a strong alignment with the mean direction, whereas when we move from a disk to oblate spheroids and then we go near to a sphere, this preferential alignment becomes weaker and weaker. But the functional dependence of the PDF on the parameters of the problem remains the same. So just as a conclusion, I think some of this study suggests or reminds the fact that the axisymmetric flow is probably a very simple framework where to study the orientation of particles, and perhaps it would be interesting to compare this kind of simple model with other more realistic simulations like in channel flows or in flows which had a mean flow and some fluctuations around it. Thank you.
So, I have a few questions. Monsieur,
if I understand correctly, the experimentalists are interested in this kind of particles because they want to measure the local vorticity of the flow, studying the correlation between the rotation of the particle and the vorticity. Mainly.
Well, there's also hope of improving heat conduction and all kinds of things. By now particles.
Yeah, but then it's nothing to do with being spherical or elliptical.
No, there is a lot to do. Because whether, their rotation helps, making some little mixing and things like this.
Okay, anyhow, I mean,
It is important.
Yeah, do you know anything about the correlation between the local vorticity and the...
Not in this case, because I know, yes, that there is this important question. Here it's orientation with respect to the mean flow. Another question is orientation with respect for the eigenvectors of the stretching, for example. Here it's less straightforward because it's difficult to obtain these directions of the stretching, of the straining. So here you can obtain, I mean, maybe it's easy to simulate because it's a simple situation, but analytically it's more difficult.
yes, so it would seem to be of interest to know whether the probability, the peaks of the probability density are associated with a minimization of the form drag. Okay, so that you can correlate what the dissipation component associated with the orientation is.
Yes, it's yes, because in the end it's that it's when one makes those assumptions of very slow, very small Reynolds number, etc. I think everything goes. The main information regarding the particle is exactly this right coefficient, and utility is related to this.
Different question. What about collective effect if you have a lot of these highly anisotropic particles? I mean,
They're tough.
hmm?
They're tough.
Yeah, it's très tough, yes, I know. But what I would like to know in particular is there a kind of density at which collective effect will become important? Do they depend a lot on the anisotropy of the particles, or are they roughly the same as for spherical particles?
Precise.
Yeah, I'm not able
The
to.
touch.
I wouldn't be able to see it.
Well known for physics.
If you look at ordering of ellipsoid revolution or spherocylinders, if they become completely needle-like, then the nematic ordering will occur at arbitrary small densities for the reason that Utama just said.
But the limiting ordering don't need to interact with each other.
Even if you take hard exclusion, just excluded volume.